My name is Kehrberg and I'm a PhD student at Bosch, and today I want to give you a presentation about how we calculate quadrature errors for MEMS gyroscopes, and especially for complex gyroscopes. So as a short outline, at first I want to present one of our test structures. Afterwards I will talk about 3 different ways to calculate these quadrature errors, and in the end I want to compare these 3 methods, how they work out. So at first have a look at this test structure. This is a test chamber gyroscope that can measure angular rate around the y-axis. It is made by the Bosch foundry process, so thereby it is made of polysilicon and is about 11 micrometer thick. We do use here the Coriolis working principle, so therefore we have 2 masses, and as you see here, we not only need masses, we need a velocity, so these masses should move, and therefore we use a resonant working principle. So we have an eigenmode that has an eigenfrequency of about 25 kilohertz, and when you apply an electrostatic forces on the comp drives on the left and right hand side, then you get these antiparallel movement of the 2 masses. And now you can use the right hand rule, and you have the velocity in this direction, then the angular rate in the second, and then you have the resulting sense amplitude and z direction that is presented here. And we also have an eigenmode that is at about 25 kilohertz, and thereby we can stimulate the sense eigenmode. And with some detection electrodes underneath these detection masses, we can sense angular rate with this sensor. So how does this angular rate sensor is influenced by quadrature? If you have a look at these drive springs that you have here, this is just the upper right corner of our sensor, then you can imagine if the cross-section of these springs would be a perfect rectangular shape, then we would have, with an in-plane drive force, a perfect in-plane sense amplitude. But whenever we have a slightly imperfect trench process, we get a minor misalignment of these side walls, as it is presented here. And these cross-section with the misalignment has the effect that whenever you have an in-plane drive force, you do not get an in-plane amplitude, you get some resulting amplitude that has a large drive amplitude, but also have a minor sense amplitude. And that is what we call quadrature. So that we get out of our imperfection also some sense amplitude. And our goal is to have methods to quickly calculate these quadrature errors inside our simulation, to find ideas to reduce the influence of quadrature effects, to find designs that are not influenced by, for example, an imperfect trench process. So how can we calculate this quadrature? There's one idea, we call it the tangents delta method, that goes back to Akar and Schell. And just to describe this method, at first we do have a drive amplitude. That is the starting point of this whole movement. This drive amplitude then will lead to a Coriolis force, that is the desired working principle. And then this Coriolis force stimulates the sense mode, and thereby we have a sense amplitude. But we have also this undesired path here, and due to our imperfect trench process, we get a parasitic amplitude in sense direction. And this parasitic amplitude can be calculated by a modal analysis with this applied imperfection. And now we can equalize these 2 amplitudes at a single point, and thereby we can find an equivalent angular rate. So by equalizing these 2 amplitudes, we can say, okay, with this imperfect trench process, we get an output signal of, for example, 1000 degrees per second or 100 degrees per second. And that is the goal of this calculation method. And the big advantage is that it is really fast. You can do this calculation within really short time. But as a disadvantage, at this point, you have to equalize amplitudes at a single point of the structure. And therefore, you need uniform amplitudes. So whenever you go back and have a look at this mode shape, the detection mask does not have the same color. So as you see here, we have some tilting and warpage, and that makes it really hard to find a representative sense amplitude. And therefore, this method is not really not really good for these type of gyroscopes. Therefore, if one point is not sufficient for the calculation, we use the whole eigenvector. So, for example, I have here a much more simpler model, not a whole gyroscope, just one bending beam. And we could assume that this bending beam is mounted here, and then we apply a force in straight that direction. But if this bending beam has these misaligned side walls, this amplitude is not only in z direction, it is an amplitude in z and in x direction. And what we can do now is that we do a second simulation without quadrature effects. Thereby we get eigenmodes that are with a strict z direction movement, and we have another eigenmode with a strict x amplitude. And what we can do now is do a least square fit to get a correlation matrix R that we can describe our eigenmode with quadrature through a superposition of eigenmodes without quadrature. So we take a lot of this mode and a little bit less of this one, and then we get a combined mode that really looks the same like this. And now we can use these correlation matrix called R to modify our stiffness matrix in the equation of motion of the system. And thereby we get a modified stiffness matrix that includes the stiffness from the quadrature effects. So what we see here is the equation of motion for the system consisting of drive mode and sense mode. And here in the spring stiffness matrix, we have these secondary element matrices elements. And once again, if we have a look here, we have this drive amplitude, and we have this desired path here, the Coriolis force, and we have the undesired path here, and thereby we get from this undesired path a spring force caused by the quadrature effects. And now we do not equalize amplitudes at a single point. In this case, we equalize forces. And thereby we can contribute to the fact that we have some mode shapes with warpage or with bending or something like that. So this is a big advantage of this method, that we can handle especially very complicated mode shapes, but there's also a big disadvantage. To get these correlation matrix R for complex mode shapes, you need to take into account with this method a large number of eigenmodes. So therefore, we have to calculate, for example, around about 100 eigenmodes to get results, and that takes really long. If you have very large finite element models, you have to wait for a really long time to get converging results, and at least you're never really sure if you have used enough eigenmodes. And therefore, we improved this method, and it is quite a simple idea, because we have recognized that it is not sufficient to apply these modification to the stiffness matrix. You also have to apply this modification to the mass matrix. And thereby, you get an inertial coupling force. So not only a spring stiffness coupling force, that is this one that was also existing in the old method. We applied a second coupling inside the mass matrix that is calculated in the same way, and thereby we get here a second path. Then we build the sum of both forces, and then once again we equalize the forces. And in the end, we can find an equivalent angular rate signal, and therefore we have an expression for our imperfect trench process that leads to this number of degrees per second output signal. As a big advantage of this one, we see that when looking here at the results, so these results are normalized for a certain reference value, which you can find here, though the calculation with a maximum number of modes. If we have a look here, we have at first the tangent delta method, so that was the first one that I presented, where we can equalize only amplitudes. That is really hard for this structure to find the real amplitude, and therefore we get a value of above 19% compared to the old reference value. So with this method, we get, so to say, wrong results. So this method doesn't work so good for this type of gyroscopes. But what we can see here is, if you use only the stiffness coupling, only the modification on the spring stiffness matrix, then we have over the number of modes for the correlation, so for the combination of different modes to build up these quadrature effects, that we have these alternating results. So we have to use, let's say, at least 100 eigenmodes. To be more exactly, we have to use 150 or 200 eigenmodes. But with the new method, we have, with just using drive and sense eigenmodes, so on the left-hand side of the diagram, we have just below around about 0.3% error. So that is quite good, and that is sufficient for our optimization. And what you see here is that when you use a larger number of modes, both methods showing, giving us the same value. So that is quite nice that we have different methods, and also if you use simpler mode shapes, so without this bending and warpage and so on, then also the tangent delta method would give us the same result. So that is the point, that these quadrature effects cannot be measured such exactly, because for measurements we would need the perfect misalignment of the sidewalls, and that is not easy to find out, because even with scanning electron microscope measurements, we have just in a nanometer range and resolution, and that is not sufficient for calculating really exact values. But in this way, we have 3 different methods, and all methods show nearly the same results, and therefore we are quite sure that we are on the right way. And that was my presentation. Just to sum it up once again, the new method is really accurate because it uses the whole structure. It is really fast because just drive and sense eigenmode are sufficient for the calculation. The method is really versatile. It can handle almost all types of gyroscopes because it compares just the eigenvectors, and you can calculate the eigenmodes of almost all types of gyroscopes. And as an outlook, we are planning further optimization of the calculation time, for example, by just using reference nodes instead of the whole number of nodes from the finite element model. So thank you for your attention, and I think we have at least a few minutes time for questions.